Good. All right, so I'm William at Hidalgo. We're going to be doing the gas turbine electrical generation system. We're going to go over the data for it. So main laboratory safety, you need proper PE. You got to return all the fuel and contaminants back to the fume hood. And there's a lot of the fuel is highly corrosive and stuff like that. You don't want to spill that. And it's very flammable. Precisely follow instructions. Try not to ask questions. Use caution and ensure adequate pre-start visual inspections are done. So our objective, we want to gain an understanding of what the turbogen actually does for the electrical generation system as a whole. Kind of want to, see what's going on, see how much power you can get from a turbine. Detailed understanding of engine and generator sensor placements, we'll go over that, it's going to be a main part. And then graphically plot all the turbogen system data as required. We'll get into that in just a few. So the main systems of this this experiment, you got your engine air intake at the front, your compressor, then you have your jet engine and power turbine, your engine thrust, transition deflector, your free turbine, and then your electrical alternator and load supply. That's where your power is going to come from the front part of your turbine. So the main things that we're going to be looking at in our data is going to be these sensors. So you got your P1 and T1 at the bottom, that's your compressor inlet, your pressure and temperature. Your P2 is going to be your pressure exit, and then your temperature exit from your compressor. T3 is going to be your turbine inlet temperature. As you can see, you got your fuel flow at the bottom, I didn't say that earlier. T4 is going to be your temperature at turbine 2, so that's what's going to be spinning your generator or your alternator as what's going on here. And then T5 is going to be the exit pressure and temperature for that second turbine that's spinning your alternator. So this is the experimental data that was collected. This was from an old experiment as ours didn't work. So the total number of data was 934 data points. I kind of looked over it, and it started and stopped a couple of times, but there was one start point that had my max RPM, so I used that. So the initial conditions, I kind of averaged that over the day, the 10/16 date, and then the date that was selected for this data, which was 3/29. We got a barometric pressure of 101.896 kPa. Your fuel density per unit volume is pretty average, that's 815. And energy content was 36.76. And the fuel used is going to be kerosene, it's what's been relatively available, that's diesel fuel. So the data selected at that point was at the time of 2,638 seconds. So the time was, that's very arbitrary, if that doesn't matter. The atmospheric pressure, which was calculated earlier, is 101 kPa. Compressor inlet pressure was 2.86. Compressor exit, 99. Turbine inlet, which is going to be important, is 100. My main engine RPM in one is 5,893 RPM. In turbine 2, you kind of take this from turbine 1 to see how close the two turbines are. So it's off by, so this one's going to come out to be 58,634 just about. That's going to be, the two turbines are pretty much spinning at the same speed, which we'll get into here. So as I said earlier, the sensors, this is all the sensor data. So T1 over time versus T2, we can see that there's a high spike in time at that's 240,000 seconds. Wait, 2,400 seconds, sorry. Then your pressure, you can see how your pressure is kind of the same versus the two. So then we go into 3 and 4. Our 3 and 4 is basically the same, but we do have a spike in P3. I didn't understand the time at the temperature at this one. I didn't understand why it dropped. And then you have your fuel flow and your RPM. So as you can see, as you increase your fuel, your RPM comes up. As you decrease, your RPM can go up as well. This is because you're heating out the engine too much, so you have, you know, excess RPM at that point. And you have your power and your N2. So N2 is our second turbine, which is going to be spinning our alternator, which is going to give our power. So as we see a spike at around 2,700 seconds, we have a spike in our power, along with after 3,000 seconds, we can see that being reflected with our power as well. So as you increase your N2 RPM, your power is going to be increased as well. It's kind of, you know, pretty equal with it. So the temperature and time versus the 3, I mean, as you can see, they're all kind of following the same. T3 kind of dips off and varies itself. I didn't understand why that happened. I wish I could have. Also with your pressure. And, you know, the results and conclusions, I wish we were able to run it, but, you know, some of the possible sources for error could have been the data retrieval from the DAC system. It's really, it takes data every second, so, you know, you might see fluctuations that you're not able to see within a second. And then your RPM lever, I know that we had an issue that, you know, Devin was our person to control the RPM, and he couldn't get it to start because he was going too fast or too slow.
Bro.
Sorry, man, you were the person. Yeah, but just, you know, pre-start procedures, you gotta be able to, you know, run that and follow it. If not, you could get fussed at pretty easily. So that's it.